Just to jog your memory again, x squared, x4, x6 to all the way x98 versus x cubed, x7, x9 to x99, there was a pattern. We knew that it was symmetrical, so quadratic, that's your x squared. The larger the power, the more square the graph looks. And we explained that because the fractional component, the larger the denominator number is, the actual smaller the number is. That's why it gets really flat and small. And the intersection is always at the 1 and 1. But symmetrical, that's one of the key things. Versus your odd powers, you remember it was cubic, asymmetrical. Okay, so instead of it being symmetrical, meaning it's a mirror image, it is now a mirror image, but upside down. So like 2 cubed versus negative 2 cubed, you get 8 or negative 8. So it's the same thing, it's just in a different direction. But you find that it's also the same, that if you went all the way to x99, the larger the power, it's the same idea again. Gets really flat in the center. And again, it crosses at 1, 1. Same idea. Okay, so negative 1 is 1 there. Right? That was for whole numbers. Now we're looking at the same thing in exercise 7a. We're just looking at fractional numbers. Instead of it being to the power of 3, well, what if it was to the power of 1/3? And then 1/5? Then 1/7, 1/9? What is the pattern? So in this first table that I've got for you here, we're going to look at x to the power of 1 on n. Rather than x to the power of n, we're now looking at 1 on n. And just focusing on positive, okay, rather than being a negative. So what if it's just 1 and 3, 1 and 2, 1 and 4, 1 and 5, 1 and 6, 1 and 7? What's the pattern? Now notice what I did here for you. When you have x to the power of a fractional power, so p on q, notice how I broke it up into 1 over q and then p on the outside. This is technically a composite function. Yeah, composite functions, you've got g of x within f of x. Why did I choose x, 1, and q inside rather than writing, because I could have done it this way. Why do you think I chose this one first? Anyone have a clue? Going back to composite functions. It is to do with whether it's defined or not defined. Now, if I chose this one, x to the power of any number, whether it's 2, 3, or 4, x to the power p, that will accept all values. The problem is that when you do a 1 on q, not all values are accepted. So that means for this composite function to be defined, it makes it much trickier. Whereas this one, again, trickier for us to know which one you have to look at it. Whereas this one, you can actually determine it straight away. Because 1 on q has a restricted domain. Once you have this implied domain, then no matter what you do to the power, it always will exist. That's why you're looking at the domain of this composite function rather than that one. This one's all real values, this one isn't. Now let's take an obvious number first. We're going to start off with a number that you're familiar with. What if I make q 2, so it's an even power? What's x to the power of half truly? What kind of graph is that? Yeah, it's a square root graph. It's a square root function. And a square root function, it's like this. So if I asked you, what is the implied domain of x to the power of half, what is the implied domain? Yeah, it's from 0 to infinity. So it's r plus including 0. So that's the difference. Had I put xp first, if I did, just x, and then times it by 2, or power of half on the outside, the problem is that you're saying it's defined in the g of x, but then it's undefined on the outside because it cannot take negative values. Okay, so what we can say now is that let's focus then. We're just going to look at q being odd. Q being even, you already knew was square root. So this is even, x to the power of half. What do you think it will look like if it's cube root? So you know the cube graph, then what's cube root look like? Because if you know what x squared graph looks like, then you can picture what a a root graph looks like, then what is cubed versus cube root? What does that look like?
Cube root is like reverse, and you can define them as well.
Yeah. If you visualize it, think about it. See that graph there? That's your cubic. This is a squared graph. So when you do the inverse with square root, it looks like this. Technically, it should look like this. That's in the square root relation, not a square root function. It's a relation because if you did a vertical line test, clearly that green graph I just drew is not a function. That's why we only take the top half and we say that's the square root function, right? Then same thing with cubes. See, cubics, it looks like an N shape, if you can kind of think of it as like an N, versus if you do the inverse, well, the inverse should then look like this. Maybe I'll do a different color. Let's do purple. You see that? Very similar to your square root graph, but because it's asymmetrical, it's cubes, okay, the denominator is odd numbers, you've got the other N. So square roots cannot take negatives, but cube roots can. So you have this sort of S shape. So N becomes an S shape for the cube roots. Now that you know that, we can explore now. Let's see what happens when I change it to all odd denominators. Set of 3. What if I had 1 on 7, 1 on 9, 1 on 99? That's the pattern. Now you can do that on a CAS or you can do it on a Desmos, but what do you think would happen? Anyone have a guess? Yeah, let's test it. So I'm going to go to Desmos. Here we go. Y equals x to the power of 1 on 3. So we've got our S shape. I change it to 7. I change it to 9. I change to 99. Exactly like what Albert said. It gets really flat. Yeah, just like the cube. So if you know your chapter 1 stuff, then looking at this, you only needed to know cube root. All right? So same thing with the square root. Had it been 2, that's a square root. Then it's 4th root, 6th root, 8th root, 98th root. Can we see that? It's the same concept, the way that you've learned. As long as you know the first basics. So if you know half, then you know all the way to 1 on 98. If you know a third, you know all the odd powers. Cool? But there is something that I want to add on top. So all these ones you should be able to predict now. So 1 on 5 versus 1 on 3rd. You can draw it here. So draw your own just so you have an understanding or remember. It's an S shape. And the only difference is it gets flatter between 1 and -1. The larger the number, the flatter that S looks. So just write that as part of your notes. But the other thing I want you to focus on then is you also have a numerator. It's not always 1 on 7. It's not always 1 on 99. What happens if I go from 1/3 to 2/3? Because the numerator matters, whether it's squared or cubed. What happens when you square? Because that's obviously a square there. If you broke this up, this is saying take your 3rd root graph, okay, cube root graph, and then square it. What happens when you square a number? It's always positive. Remember, cube root can have negative values. So if you take all of these points and you square them, these negative values become positive. So what do I expect these cube root graphs when it's squared? What should it look like? It should look like one of those birds that you draw. You know, when you do the picture frames in primary school, when you sort of do it, I'm going to just do it here so you can see a little bird when you draw the bird. But that makes sense because everything gets squared, it gets larger, but not only that, the negatives become positive. But that's not the same for 3/3. What happens if I go, instead of 2/3, what if it becomes 3/3? What does that look like? This is straight up line. But this is really interesting because 3/3 looks like that. We know that's a linear graph, right? 1/3, I'm just going to do it underneath. You should see a pattern here. 1/3, can you see how it's below the straight line? And this is curved this way. So if I asked you now, what do you think a 4/3 would look like? it's bigger than 1, what do you think it would look like now? Yeah. Okay, so here we go. Let's have a look. If I change this to 4/3, 4/3, remember it's a squared, it's multiples of 2, so it's got that symmetrical bird shape. But watch what happens. Can you see the shape? Instead of looking downwards, it looks a bit upwards. Can you see that? How it's curving upwards. So if I changed it to 12, can you see how it's kind of looking? Well, 12/3 is actually a quartic. Let's make it 14. Can you see how it's curving up rather than curving towards the x-axis? But what's interesting is that when I change it to 5 cubes, the 5 cubes is going away from that line that we had. We had 3 on 3, so here's 3 on 3. You see that blue line? It's curving away from that line. Versus if I changed it back to 2. Oh, sorry, what was the number? 1. See, 1 goes down, 1 goes above. See that? And that will be the same even if I change the denominator to 5. So 5 on 5. So if I just change this now back to 1/5. So that's your 1/5. Here's your 5 on 5. I'm just going to go down. X to the power of 5 on 5. So that's the green line. Watch what happens when I change instead of 5 on 5 and I make it 7 on 5. Can you see that? When it's below the 5 on 5, which makes it a nice linear line, it's curving closer to the x-axis. When it's above the 5 on 5, so 7 on 5, 9 on 5, 11 on 5, it should get closer to the y-axis. Write those notes down for yourself so you can see the pattern. Because that's what we're looking for. Yeah? So write it down. Write in your notes here. So there's this difference between when it's squared. What's happening with squared is it should be symmetrical, not asymmetrical. And we expect it, the S shape, to curve around. It should be getting closer to the x-axis. But if I did it to the power of 4 on 3, then you'll find that it curves the other way. Starts to look like it's curving towards the y-axis, if that was 4 on 3. Okay, because it's bigger than the 1 on 1. So instead of closer to the x-axis, it's closer to the y-axis. And that's why when I do 8 on 5, what do you expect x to the power of 8 on 5 looks like? Have a go. Draw it first. Let's see if your prediction's correct. What does 8 on 5 look like? What do you think 8 on 5 looks like? All right, let's see. So you know 4 on 3, so you should be able to figure out 8 on 5. So here we go. Here's 8 on 5. I'm going to change it to 8. Hands up if you got something in that vicinity. So it should be symmetrical and it should be curving towards the y-axis. Those are the 2 hints. Very good. All right. Here we go. So it should be curving towards the y-axis rather than looking like a bird shape. Okay? All right. So that's the positive value. So you can write your own notes here just so that you remember. Okay? So that's just to help you write any notes there for yourself, how you would remember what I just described. So we know that what kind of graph do you expect when the denominator is odd? You can expect it to be asymmetrical. You can expect it to be asymmetrical. So something like this, your S shape. But then it depends, we haven't talked about the numerator. So here, how does it change when the numerator is even? Well, we know that if it's even, it squares every value so that it becomes symmetrical. So when it becomes symmetrical, we expect this. Put a note on the side. Note the rational number or the fraction whenever it becomes 1. When does it become 5 on 5, 4 on 4, or 6 on 6, or 7 on 7? Look for that linear graph because that literally determines when it curves closer to the y-axis or the x-axis. So e.g. x to the power of 5 on 5. So therefore, x to the power of 7 on 5 and x to the power of 3 on 5, they're different. So one's a straight line, one curves closer to the y-axis, and one curves closer to the x-axis. Okay, so just something like that. That's how I would write it for my own self, but you need to detail it more so that you understand and do that. Yes? Yeah, sure. All right. Once you've done that, I'm going to pause the video for a second, and I want you to... Here's one 7th. Here's one 9th. And here's one 99. Same idea. One gets super close to the y-axis, and one is always going to be much further away from the x-axis. As in, it's always bigger, so it gets flat. Okay, at that 1 mark. So negative 1 and 1. Okay, so negative 1 and 1, that's where it's determined. Write your own notes for that one. What happens when you square and then do to the power of 4? As I shown you before, squared, 4, 6, 8. Actually, I shouldn't do 99, just so you can visualize it. You can see that it's still the same as what we saw with a square. So if I go to 10, if I go to 12, you can see it's always going to be below. Well, at some point when you square it too much, then obviously it goes below the 1 on x line. Okay. All right, team. This is what I meant. Exercise 7A. You don't have to remember all of these graphs, but what do you take out of it? 7A is for you to analyze. Okay, so when they give you, they're not going to give you the ones I've given you so far, but you do need to be able to analyze when it's squared, when it's cubed, when it's negative, when it's positive, in their own different variations. The way I've tried to write the notes is to help guide you on your thinking to analyze the equations. Okay? That's what you take out of 7A. That's the essence. Don't have to memorize every single example I just gave you. It was for you to take out the essence. If I gave you a calculator, could you come to a conclusion by describing what would the function do? Okay, that's the idea. All right, team. It's almost 11. I think I'm only going to do one bit of notes, and then we'll call it for today. I will continue 7B, okay? Can you flip to 7B for me? 7B. Let's fill in some notes. It's only one little bit that I want to make sure you have a clue. All right, here we go. Let's revise again. Chapter 1. 2 of the key components of Chapter 1. 1E was composite. 1F was inverse functions. These are your 2 conditions for composite functions. And then for inverse functions, we know that it's when the inverse is equal to the y, or y equals x. So f of y equals to x is by definition. But we also know domain of the original functions is equal to range of the inverse. Fill that in. And then the range of your original function is equal to the domain of your inverse. Okay, so that's just a quick review of the definitions that you must know from Chapter 1. Today, I'm adding on just this little bit here. Can I get a show of hands who've heard of the term strictly increasing and decreasing? Okay, good. Because this is more of an exam question. Okay, so they usually ask it in exams. It's a very small component in your textbook, hence why I'm sort of pointing it towards you so that you know it's here. So strictly increasing and decreasing, by definition, it literally just means if a number is bigger than the previous number, it's strictly increasing if and only if the y value for that bigger number is also bigger than the y value for the smaller number. So on a graphical sense, this is what I'm saying. I'm saying if you picked A is bigger than B, as long as f of A, so let's say this is f of A, is also bigger than f of B. For all x values within that domain. Okay, so wherever that domain is, if for all values, it is true that if you had x is bigger than b, and y is also, for that particular a, is bigger than b, the y value for b, then that's called strictly increasing. Why is this important, or why do they chuck into the exams? There's only one small thing. Do you know when it comes to derivatives? Let's see, testing your memory on derivatives. I know we haven't done it yet. Let's test your memory on derivatives. You know when you do derivatives, at the very top of the turning point, what do we know about the derivatives again? Equals 0. So f dash must equal to 0, right? So when they ask you, back then they'll say, describe when is f dash of x greater than 0. So this is when this is when the gradient equals 0. When, so let's just say this is at x equals 2. When will the gradient be positive? So look at this graph. When will the gradient be positive? How would you describe it? Because this is what the examiners would do. They'll say, define when, or state the domain, or state the x values for such that the gradient is greater than 0. What would you say? Very good. So that key part there that Rango just said there, negative infinity all the way up to 2. So I'm essentially saying, when will you have a positive gradient? Well, all these tangent lines have a positive gradient. All of this is positive, positive, positive up until this point, that's 0. And if I ask for the domain, what you just said to me is the domain is everything from negative infinity up to 2, but the key part was here. You don't include 2, right? So here you'd say not include 2. But when I ask you for strictly increasing, technically every x value has then a higher y value. So all of this is increasing, increasing, increasing. The question is, do you include the 2? Yes, you would. You would include the 2 if it's asking for strictly increasing, because the y value at 2 is bigger than the y value before. 2 is bigger than 1.99, and the y value of 2 is bigger than the y value of 1.99. You would include it. So when they ask for strictly increasing the domain, the only difference is then we say it equals to that endpoint. That's just by definition. Cool? Some other questions in the exams is then they say show that it is strictly increasing or decreasing, and that's tricky. So the next example I got just underneath that, that's the one that I'm doing with you. I did a lot of little notes in between to help guide you. That one's tricky, but I'm not going to do it today just because it's a lot of explanation today. Okay, so today what I want you to write in part of your notes, by definition, A greater than B, f of A greater than f of B for that domain. If it's true for every single value, you call that strictly increasing. And it only matters when you do the exam question, it gets to the domain whether you include the endpoint or you don't. That's really when it happens. Okay? So here, decreasing is the other way. If A is greater than B, but then f of A is less than f of B, essentially it's the other way around. The y value for A is smaller than the y value for B. Okay? Now here's a note that is in chapter 9 that you will fill in, but it's just nice to know. This is the key point to note because examiners will rely on that you know this. If the function is strictly increasing or decreasing, then it is a one-to-one function. Which if you think about it logically, it makes sense, right? Because if it's always continuously growing between domain A to B, well, of course it's a one-to-one. Yeah, because otherwise if it curves down, then it's not strictly increasing or decreasing. It always has to either increase or always has to decrease for every single value. So of course it's a one-to-one. Yeah? Last bit. This is from chapter 9. So even if you don't remember it now, when we get to chapter 9, I'll have that definition again. But if you do the derivative and it's greater than 0 for an interval or the domain, then the function is strictly increasing within that domain. And that's one of the ways that you can prove if a function is strictly increasing or decreasing over a certain interval, you do the derivative. But that's for chapter 9. Chapter 7, you do a different way, okay? Which is the example I've got here for VCAR 2016. I'm guiding you in there. But if we didn't do the derivatives version, then that's what you would have to do. Okay, so what's here? If the gradient is negative, over the interval, then it is strictly decreasing. So these 2 points will help you when it comes to an exam question that asks you to show or prove finding the derivative will be helpful. Otherwise, you can do what I'm going to show you next lesson for this one. You can have a go with that one if you want to feel it out, see if you can feel them out. But I'll guide you through this next session. Okay? All right, that's it, team. It's 11:04. You've got about 25 minutes of your time to work on either chapter 6 or you can start on chapter 7.